first part of this plenary session was about testimonials contributed from the industry. The second part is more university and research, so they will tell us, or they will contribute a different perspective to the same type of problems. The first speaker is Dr. Falkenberger, who is an assistant professor at the Hochschule in Ulm in the Laboratory for Structural Mechanics and Acoustics. Again, I had the chance to listen to your presentation sometimes, and it was exciting. So this is one of the reasons why I invited you to present. The title is quite long, so it's up to you to read it.
Thank you very much. Thank you very much. Welcome to my presentation today. So today I'm going to tell you a little bit of the actual research project we're working on, the calculation of the sound radiation of gearboxes. So the focus of today's presentation is going to be the validation of the dynamic bearing forces in the gearboxes, because the dynamic bearing forces is the excitation of the gearbox if it's vibrating. So I'm going to start at this block here with what do we do and how do we do it. And the second one is going to be how do we calculate the dynamic bearing forces. Third part is going to be the how to measure dynamic bearing forces, and last but not least, the comparison of both. So I'm going to try to take you from the original gearbox, setting up the models, calculate dynamic bearing forces, and same with measurement, setting up test bench, and show you measurement. Okay, so what do we do? What we do is we calculate the sound radiation of gearboxes. Basically, it's done like, you know, the gearbox is sitting in the powertrain and is excited through many different noisemakers. So there's the combustion noise, which is exciting through the engine block, unbalances of the shaft, and of course through tooth engagement, which happens inside the gearbox. And what we do is we cut the gearbox out of the powertrain and we simulate the sound radiation of it. So if you cut it out, the only excitation which still remains is through tooth engagement, which happens right here. So the vibrations are occurring here, are traveling through the gear wheels, shafts and bearings, causing the gearbox housing to vibrate. And how we simulate this is going to show you this slide. So basically, we have a calculation chain, and the calculation chain is basically the 4 purple boxes right here. So it starts with modal analysis, but before you can start doing your modal analysis, you need your finite element model. And to get your finite element model, I mean, you know, CAD data, take your data and mesh it, or you can use a reverse engineering process to get your finite element model. If you have a finite element model, you can do your modal analysis. The modal analysis gives you your properties of your structure, vibrating properties, so the eigenfrequencies and the shapes of it. The second step is going to be in a multi-body simulation, where we are calculating dynamic bearing forces, which are the excitation of the gearbox. The structure-bound noise uses the eigenfrequencies of the shapes and the excitation as bearing forces to calculate the velocities of your structure surface. And if you have the velocities, you can easily calculate the sound radiation of your structure, in this case the gearbox. So one of the best parts of this calculation chain is that we can validate every calculation step with a measurement. So for modal analysis, as you know, experimental modal analysis. For the multi-body simulation, we set up the test bench. And the same happens for structure-bound noise or sound radiations with microphones, as you know. As I said, today's focus is going to be the validation of the dynamic bearing forces. So how do we calculate the dynamic bearing forces? Let's start with the original gearbox. So this is the original gearbox what we have. It's a 6-speed manual gearbox which is doing its job in mid-size cars. And to keep it more simple, what we did is we removed all the original parts of this gearbox. So we removed all the gear wheels, bearings and shafts. And we designed a completely new powertrain with only one gear wheel section. And This gearbox consists of two parts, as you can see. This is one part and the other one. And we used a reverse engineering process to refeed this structure back into the computer. And for the 3D scanner, for the recognition of this part, needs this white powder. So this is the reason for this white powder. Okay, so if we refeed it and scanned it, we meshed it and got our 3D finite element model. This got like 20 million degrees of freedom. And as I said, we designed a completely new powertrain. This sits inside this gearbox, of course. And the powertrain, as you see, is very simple setup. It's got only 2 shafts, 1 gear wheel section, and 4 bearing positions. The shafts are set up with beam elements to keep the bending, and the contact between the 2 gear wheels, I used a 3D gear wheel contact, which sits right here. And this contact works like this, that the surfaces of the teeth are divided into triangular patches, and the normal direction of the triangular patches are defining the direction of the force which is traveling from one gear wheel to the other. But no more detail, it's going to be too complicated maybe. Okay, everybody who's simulating, I guess there's a couple of people right here, knows that a simulation of a bearing could be challenging as well. So what I did is I took an isolated look just at the bearing. So isolated look means I just set up this model. This model consists of 3 rigid elements: the outer ring, rolling elements, and the rigid inner ring. These rolling elements are connected with spring damping elements, which are approximating the bearing cage, as you know. Then I fixed the outer ring to the ground, so it's standing still, and the inner ring was spinning with 1000 RPMs, and I added a force of 1000 Newton. And then I plotted the force at the outer ring, dynamic bearing force, and this looks like this. Hopefully. Okay, so we're in frequency domain, and what we see is lots of peaks, which I have to explain what it means. So if this bearing, this special geometry of this bearing is spinning with 1000 RPMs, the rolling element frequency, because these rolling elements are passing the area of force right here, these rolling elements are passing this area with 95 Hertz at this revolution speed. So we get this peak here at 95 Hertz. And because it's an impulse sequence, the multiples of it are occurring as well. So the multiples of it means 95 times 2 times 3 times 4. So this is a normal behavior. But we found this, I call it funny frequency, because there is actually no mechanical reason for this frequency. So I was like, okay, where is this frequency coming from? There should be a reason. Is it a numerical problem or what happens here? So I investigated the approximated bearing cage, because it was the first thought that this might be the frequency of the bearing cage. Then I checked the force which was acting in this spring, and if you plot this force, you come to this graph and you see an oscillating force right here. And if you measure the period of time, you come to a 0.147 seconds, which correlates with the frequency of the bearing cage. So this is still the funny frequency, and it's not the bearing cage. So there should be another reason. Another good thing what you can see in this force is these little peaks right here. If you measure this time difference between these 2 little peaks, you come to a 0.011 seconds, which correlates with the 95 Hertz, which is the rolling element frequency. So this plot shows us that the dynamic behavior of this bearing model works pretty well. But there's the funny frequency is still there. So what happens here? So another thing, the second thing I did is I checked the contact area right in between the rolling element and the inner ring. And because multi-body simulation, you know, you can calculate every force wherever you want. So you can plot the friction force, which is acting in between this contact. And if you plot this force, you come to this blue line right here. And if we measure time distance between these two peaks and these two peaks, again, is the bearing cage frequency, which is true. And when one rolling element is spinning around and entering the area of force, maybe here, the entrance impact happens. And if this rolling element leaves the area of force, the exit impact happens again. That's the reason for the two peaks. Then I started adding up all the friction forces of all the 14 rolling elements. And if you sum up all the forces in the contacts and plot it into one plot, you come to this result. Now you see that obviously the friction force is oscillating. And if you measure the period of time of this oscillating frequency, you come to the 0.12 second, and this correlates exactly with this funny frequency, I called it. So now the name for this funny frequency is a oscillating friction force. So why is this happening? Is the next question. If you find the reason, you have to understand why is this happening here. Then you have to think about how is the friction model implemented in this solver. So the friction model is like this, that the solver checks the relative velocities between two bodies. And because of this relative velocity, the friction coefficient is determined, and then the friction force occurs. And the oscillating is because we have a slip or a frequency. When this inner ring is spinning, the frequency is changing in this kind of frequency. So the friction force, 8.3 Hertz, is now not a true or not a good behavior. So what is this telling us? If we go back to this plot of the forces, 95 Hertz, multiples of it, this is what we want to have. We don't want to have this friction force here, this oscillating friction force, but we don't have a solution right now for this, but we know and we understand the model better because we know where it comes from. And if you see this frequency somewhere else in your powertrain model, you can think and understand why this is happening here. Okay, so this is again the powertrain which we designed, just one gearbox section, 4 bearing positions, and this yellow and green block here is a block of steel, 2 blocks of steel, which is the bearing force measurement device. I'm going to tell you a little later what this is and how this works, but this is what I want to tell you. We're going to simulate this too. And with this virtual sensor, we calculate the dynamic bearing forces right on this point here. And the dynamic bearing forces looks like this. So the calculation was done at an operation point at 1000 RPMs and 60 Newton meters. And because of the number of teeth, we come to a tooth meshing frequency of 500 Hertz, which we see here. And impact series, as you know, multiples of it are occurring as well. Have to occur, they do. And what happens if we zoom into this area right here to get a closer view if our model works? So now we have frequency to name again between 2200 and 1800 Hertz, tooth meshing frequency, and we see side bands through the bearings because every shaft of the powertrain contains 2 bearings, different rolling element frequencies, so we have to see side bands from the bearings right here and here. So if you measure the frequency between the 2000 Hertz right here and this 1920 something, this is exactly the rolling element frequency what we have in the bearing. So obviously our model works because the tooth engagement, there is the excitation occurring and is traveling through the model, through the beam elements of the shafts and the bearings, causing the gearbox housing to vibrate. So now we know it works. But you know, every simulation is only as good as the reality. So how do we measure dynamic bearing forces? So we started setting up a gearbox test bench. This gearbox test bench basically consists of 2 electric engines, 40 kilowatts of power maybe. This is the actual gearbox, as you know it from slides before. In the back of the test bench is sitting, you cannot see the tank, there is a lubricant condition unit. So we have a oil which is heated up. We can set the temperature of the oil which lubricates the gear wheels. And we can set different viscosities of the oil, and we can investigate different viscosities and the influences of the sound radiations and of the dynamic bearing forces. Okay, let's take a look inside the gearbox, because this is the place where dynamic bearing force is measured. So what you see is, I removed this part of the gearbox to get a look at the shafts. So these are the two shafts. You might remember the multi-body simulation model. This is the same model, and we set it up right here. So this is gearbox section, there is bearings position, and right here is the gearbox, the dynamic bearing force measurement device. To get a closer look, let me remove this shaft. So now you see this block of steel. It was the yellow one in the multi-body simulation model. So this block of steel sits in the original bearing seat of the gearbox housing. So it is a press fit and is connected to the gearbox housing. These little things here are mini piezoelectric force sensors, and every sensor can record the dynamic bearing force in 3 directions. Okay, let's put the powertrain back together. So this is another view from the same powertrain, just to let you know, to understand how this works. This is maybe not too easy to follow how it works. So again, we have these 2 shafts, bearings positions right here and here, and this is dynamic bearing force measurement device. So this is block of steel number 1, which is connected to the gearbox. So this is a press fit right here in the original bearing seat. The second block of steel actually contains the bearing of this shaft. So what we did is we moved the bearing from this place to this place, and right in this gap here between these 2 blocks of steel, there is sitting the piezoelectric force sensor. So we are sitting with the bearing force measurement device right in the power flow. So usually you measure with like acceleration sensors. You put your sensor on your structure and you measure not directly, you measure indirect. And this is a new approach of measuring dynamic bearing forces directly in the interrupted power flow. Okay, now we want to see how this dynamic bearing force looks like. Again, this is the multi-body simulation model. Just to let you know, this is exactly the same bearing force measurement device right here and here. Okay, so this is a measured dynamic bearing force, same operation point as the simulation. Again, we come to the 500 Hertz of the tooth meshing frequency. We see multiples of it. And again, what else do we see right here? These 2 peaks are coming from the shafts, because the shafts are still having some imbalances, and these are producing forces in their frequency which they are spinning. This is the reason why we have 2 peaks right here, because we have 2 shafts. What happens if we zoom in right here at 1500 Hertz? Okay, so now it's going to be complicated, because there's lots of little peaks I have to explain. This is tooth meshing frequency. Now we know where it comes from. These are side bends occurred through the shafts, caused by the shafts. They are occurring right here. Side bends is a amplitude modulating of the dynamic bearing force. So what is happening here? If you measure the distance between this frequency and this frequency, you see it is maybe like 15, 16 Hertz, and it's exactly the frequency of the spinning shafts. So this is a true behavior. And what else do we see? We are having a beat frequency. What is a beat frequency? Beat frequency is a frequency which occurs when 2 shafts are spinning almost with the same frequency. So if you have shaft number 1 is spinning with 10 Hertz, shaft number 2 is spinning with 12 Hertz, difference is 2 Hertz, so the beat frequency is going to be the 2 Hertz. And this beat frequency produces side bands as well, all over the frequency band. And we can measure this bearing right here. Imagine we are below 1 Newton right here, so very sensitive sensors. Okay, so now we know how we calculate dynamic bearing forces, and we know how we measure dynamic bearing forces. What happens if we do the most challenging thing here, comparing? So the red curve is the measured. As you know, we have the imbalance of the shafts right here. This is always one point where you can recognize which one is the measured and which one is the calculated curve. The black one is the calculated. We don't have any imbalance in our model because our model is perfect, as yours model as well. So we have, again, tooth matching frequencies which are matching very well, but we don't see very much right here, so let's zoom in again. what you see is what you get. We have tooth meshing frequencies right here. As I said, the red curve is measured, so we have all the side bands through the shafts and beat frequencies right here. And we measure bearings right here, and we simulate the bearings. So if you put the measured and the calculated dynamic bearing forces into one plot, you see most of the time big differences. But remember, the model we have, there is no gearbox housing implemented. It is a simplified model with easy contacts. For a simulation of this easy model, there are like 14 days running, so it is not too easy to do parametric studies. Okay, so what is the result? The result is we are in a good way. We are having a very good model of our powertrain because dynamics behavior is working, but still not over yet and still going. But at least we could say about the dynamic bearing force, yes, we can. Thank you very much.